Today, we're unlocking some serious nanoscale secrets using what is arguably one of the coolest, most powerful analytical techniques in materials science. I'm talking about X-ray diffraction, or XRD. If you've ever found yourself wondering how on earth we measure things that are literally thousands of times smaller than a single human hair, well, you're in exactly the right place. We're going to decode the hidden structure of materials and see exactly how this incredible tool pulls it off.
Let's just dive right in. So, in the lab, we're pretty used to thinking of an XRD pattern as a simple fingerprint, right? It's our go-to way to identify exactly what phases are in a sample just by looking at where the peaks pop up. But here's the real secret. Those peaks, they're actually doing double duty. It turns out that their actual width, like literally how fat or skinny that peak is, holds the absolute secret to measuring the size of crystalline domains. Here's our roadmap for this macro to micro journey. We'll start with the crystallite identity crisis, decode the Scherrer equation, and then walk through a quick 6-step measurement guide. After that, we'll crunch some actual numbers, look at the culprits of peak broadening, and wrap it all up with real-world nanoscale applications. All right, let's break it down.
Section 1. The crystallite identity crisis. Particle versus crystallite.
We really need to kick things off by clearing up a super common misconception in the lab, and it's absolutely crucial. Understanding the difference between particle size and crystallite size. When you're looking at a sample under an electron microscope like an SEM or TEM, what you are physically seeing is the particle size. But when you run that exact same sample through an X-ray diffractometer, the data you're getting back is calculating the crystallite size. And trust me, these two things are almost never the same number.
To picture this, imagine a massive 500 nanometer particle. Under a microscope, it just looks like one big solid gray chunk. But inside, that same 500 nanometer particle might actually be made up of dozens of much smaller, highly ordered blocks. Those individual blocks are the crystallites, the coherently diffracting domains. And they might be tiny, like just 20 nanometers across. So as the crystallite size shrinks, those XRD peaks get broader. Remember, XRD is measuring those tiny internal blocks, not the giant chunk they make up.
Moving on to Section 2. Decoding the Scherrer equation. Decoding the math.
Now that we know exactly what we're measuring, let's talk about the mathematical magic that makes it all possible. Enter the Scherrer equation. Now I know it looks like a bit of alphabet soup at first glance, but I promise you, it's just a simple recipe. D is the crystallite size in nanometers. That's what we want to find. K is just a shape factor, usually hanging around 0.9. That Greek letter lambda, that's our X-ray wavelength. And down at the bottom, we have beta, which was our peak width, multiplied by the cosine of theta, our Bragg angle. That is literally it. Just plug in those 4 simple variables, and you can calculate that invisible crystallite size. But the real MVP of this entire equation, that would be beta, otherwise known as the full width at half maximum, or FHWM. Think of an XRD peak like a mountain on a graph. You find the absolute summit, its maximum intensity, and you hike exactly halfway down. The distance straight across the mountain at that half height line, that's your FHWM. And here is a massive pro tip from the lab. It is absolutely critical that this beta value is converted into radians before you do any math. Not degrees, radians.
All right, Section 3, the 6-step measurement guide, a practical XRD walkthrough.
Let's take all this theory and turn it into something you can actually use. Here's how you tackle real lab data in 6 straightforward steps. First up, collect your XRD pattern. You really need high-quality data here. Good count rate, low noise, the whole shebang. Second, pick a strong, isolated peak. You want it well separated from the others so your width measurement doesn't get messed up. Third, measure that full width at half maximum we just talked about, which will currently be in degrees. Step 4, and seriously don't forget this one, convert that FWHM into radians by multiplying by pi over 180. Fifth, grab your peak position. XRD graphs usually spit out 2 theta, right? So you have to divide that number right in half to get the true Bragg angle theta. And finally, step 6, just plug those numbers into the Scherrer equation and find your crystallite size.
Section 4. Crunching the numbers. Let's look at a concrete example.
Because theory is great and all, but actually doing it is better. Let's put those 6 steps into practice. Say our lab equipment gives us a peak position, our 2 theta, of 36.20 degrees and a measured FWMM of 0.40 degrees. We're using a standard X-ray wavelength of 0.15406 nanometers, and our shape factor is 0.9. Okay, let's prep those variables. We take that 2 theta of 36.20 and chop it in half, which gives us a true theta of 18.10 degrees.
Next, we convert our beta. So 0.40 degrees times pi over 180, that gives us 0.00698 radians. Now we literally just drop them into the formula. Multiply 0.9 by 0.15406 for the top part of our fraction, and on the bottom, multiply our radians, 0.00698, by the cosine of 18.10 degrees.
And when we crunch those numbers, boom, 19.6 nanometers. Just like that, we figured out that the coherent diffracting domains hiding inside our sample are roughly 19.6 nanometers across. It resolves perfectly. See? The math isn't some dark art. It's just a totally methodical way of applying your lab variables.
Which brings us to Section 5, the culprits of peak broadening, looking beyond crystallite size.
Okay, time for a little bit of a plot twist. It turns out small crystallite size is not the only thing that can cause an XRD peak to get wider. The Scherrer equation basically assumes that the sole reason your peak is wide is because your crystallites are tiny, like under 100 nanometers tiny. But in the real world, your observed peak width is actually a mix of size broadening, strain broadening, and even instrumental broadening. If the crystal lattice is under physical strain or it's full of defects and dislocations, that peak is going to widen. Even the XRD machine itself naturally widens the peak a bit. That's why for super accurate results, scientists have to correct for the machine using a standard material. And if they really need to separate the size and strain effects, they'll use something called a Williamson-Hall analysis.
This really highlights how we interpret these patterns when we're just glancing at them. A really sharp, narrow peak, that tells you right away you're dealing with large, well-ordered crystallites with very low strain. It's highly crystalline. Now, a broader peak, that points to a nanocrystalline structure, smaller crystallites, and probably some strain in there too. But what about a massive, broad hump? That means the material is amorphous. It has basically zero long-range order. The atoms have, for all intents and purposes, just given up on being organized.
Finally, Section 6, Real-World Nanoscale Applications, Nanoscale Engineering in Action. So we've spent a good chunk of time in the weeds with microscopic math, but let's zoom out for a second. Why does all of this actually matter? Well, knowing the exact crystallite size is absolutely 100% critical for modern engineering. Material properties change drastically at the nanoscale. The Scherrer equation is the simple yet incredibly powerful tool used across so many fields. Take catalysts, for example. Smaller crystallites mean way more surface area for chemical reactions. Or batteries. Crystallite size directly impacts how efficiently lithium ions can physically move in and out of the electrodes, which literally dictates how fast your phone charges. From advanced ceramics to thin films to metal alloys, hitting that structural perfection at the nanoscale completely dictates how things perform in our macro world. So as we wrap up this explainer, I want to leave you with this. We interact with jaw-dropping technology every single day, and most of the time we're completely oblivious to the invisible nanoscale engineering making it all happen. So the next time you use a high-tech battery or read about some wild breakthrough in nanomaterials, ask yourself, how much of that power, how much of that sheer efficiency is secretly hiding inside a coherently diffracting domain that's just 20 nanometers wide? And hey, remember, thanks to XRD and a little bit of math, you now know exactly how to measure it. Keep exploring, keep asking questions, and I'll catch you next time.